Okay, YouTube, in our last couple of videos, we've looked at how we can multiply and divide complex numbers if they are written in polar form. That is to say, this r cosine of theta plus I sine of theta form, or more succinctly, we could say this r cis theta form. So when they're written in this r cis theta form, it's really kind of a convenience because when we multiply and divide them, we've seen how easily this can be done. When we're raising things to a power, the neat thing about this is basically we could repeat multiply, basically. We could say that raising something to a power is really just multiplying it by itself over and over again. So what we're going to do is we're going to use our knowledge of multiplying two complex numbers in standard form, where we know that when we multiply two complex numbers in standard form, we would multiply, okay, their modulus values and then add together their arguments. If we extend that here to what we see here, what would happen if we were to take, say for instance, RCIS theta and square it? In other words, we would be taking RCIS theta times RCIS theta. Now the interesting thing here is what ends up happening is that we would multiply our arguments out in front, our modulus values up front, excuse me. So we would say that z times z, or z squared, would be r times r, or r squared. And then what we see happening here is we would have to take this theta and add it to this theta. But because they're the same thing, theta plus theta, we would just get 2 theta. And so interestingly, we can say that if you took a complex number z squared and took that number times itself, you would really get the modulus times itself and then the argument plus itself. And so however many of the argument you have is equal to the power that we had, and whatever power we raise to the modulus to is the same as the power we have over here. So again, what if we were to say z cubed? One way to look at this is we could take our result from z squared here, which is this r squared cosine 2 theta plus I sine 2 theta, and take it times another r cosine I sine theta. But what we get is basically r to the second times r to the first is r to the third. So again, z cubed, we would cube the modulus value. And then what we get is really this power times the theta here, because we'd be taking 2 theta plus 1 theta is really 3 theta. So this rule could basically, we could see a pattern get extended here. Every time we raise a complex number, we can write this here. We say z, if z is equal to r cosine I sine of theta, then z to the nth, more generally speaking, would be our modulus times itself n times. And then what we would be doing is taking this angle plus itself n times. And so this theorem, I suppose, right here, we accredit it to a French mathematician here, Abraham DeMoivre. And that's, I guess, how I say the gentleman's name, DeMoivre. But, yeah, I suppose you could say how you like. DeMoivre is pretty easy to pronounce, though. But we'd say DeMoivre's theorem, basically what it states is, given any complex number, r cis theta, or r cosine theta plus I sine theta, but as long as it's in polar form, if n is a positive integer, or some positive counting number, then we'd say z to the nth power is always z to the n, which is really this r cis theta to the n. I'm going to rewrite this here. This is r cis theta to the n power. But basically what we're going to do is we're going to take our modulus and raise it to that power. So we're going to raise the modulus to the power given. Okay, so if we're raising it to the second power, we'll square it. And then what we'll do is we will multiply the argument by the power. And by multiplying the argument by the power here, you can see that r to the n times cosine n theta plus I sine n theta. By multiplying by n, we're really adding theta to itself n number of times, however many times we add this number to itself. So what we can see here is this. In this example, we say it says find 2 cosine of 20 degrees plus I sine 20 degrees to the 6th power, and also write your answer in rectangular form. So we're going to take this in 2 pieces. The first thing I want to do is essentially this. We could say this is the number, if we abbreviate it here, 2 cosine I sine of 20 degrees. And we're going to raise this to the 6th power. Now, I don't need to write this out 6 times to tell you that really what we're doing is taking this number times itself 6 times. So according to DeMoivre's theorem, what we're going to do is we're going to take our value of r here, r, and we're going to raise it to the nth power because we would have taken 2 times itself 6 times. And then with our argument here, since we would have added 20 to itself 6 times, we're going to say n times whatever that theta is right there. And so our result here is 2 to the 6th, and certainly we could grab a calculator here to figure this out. We say 2 to the power of 6 is 2 to the power of 6. Let's see if I can get this to work here. Is 64. So we say 64, And then if we were to take 6 times 20 here, what we get is 120 degrees. Now, I'm going to put a box around this, and I'm going to make a little note here. If the resulting argument is over 2 pi or 360 degrees, then rewrite as a coterminal angle between 0 and 2 pi. There was 0 degrees and 360 degrees. And so essentially we say that all direction angles should be some answer between 0 and 360. That is to say that if we would have gotten a 420 degree angle, that would have been 360 degrees plus another 60 here, then really we would have said, you know what, let's just call this 60 degrees because it gets us to the same spot. So checking out this example down here, what I'd like for you to do is go ahead and raise 2 CIS 30 to the 5th power and see what you get. When you're ready to take a look at what the result is here, let's go ahead and hit play on your video. So we have 2 CIS 30 to the 5th power. According to DeMoivre's theorem, we'll raise our modulus to that power, and then we'll take our argument times that power. So we have 5 times 30 degrees. So really 2 to the 5th, that would be, you know, half of 2 to the 6th, because we would take 2 to the 5th times 2 to get 64. So basically 32, and we could check that on a calculator, but our argument here is 150 degrees. And so because this isn't over 360 or it's not negative, we could say that this is our result right here. Now on both of these answers, one thing that we were asked to do, and this was kind of the second part of our problem here, was asked to write our answers back in rectangular form. And so one thing that I want to say here is this: if we have an answer in rectangular form, rectangular, okay, this is that form that tells us we would go A units on our real axis, okay, and B units on our imaginary axis and draw a dot to represent this point. If we want to go from rectangular form back into, you know, polar form, or from polar form into rectangular form, that is to say, if we know theta and we know r and we want to find A and we want to find B, then let's recall that A is always going to be r cosine of theta, and B is going to be equal to the r sine of theta. So with these right here, really what we're looking at is, with this example up here, and I'm going to scroll down just so that I have some room, and I'll even put this in a different color for us here. But remember that if we want to convert back from polar form into standard form, or into rectangular form here, so we have Z is 64 CIS 120 degrees. Then really what we're going to do is this: we're going to find r cosine theta and r sine theta, and the convenient way to do this, as a matter of fact, is just to write this as 64 cosine of 120 degrees plus I times the sine of 120 degrees. And what we're going to do is we're just going to distribute this through and evaluate for these values right here. So we would say we get 64 cosine of 120 degrees, and I'm going to mark this down as our A value here, plus now we get 64, and I'm going to write sine of 120 degrees right here. I'm going to tail the I off over here, but I'm going to refer to this as like our BI portion of our number right there. So we just need to evaluate for the cosine of 120 and the sine of 120. And with respect to those angles right there, let's go ahead and say something about those. 120 degrees, of course, would be this angle right here, 120 degrees. And if we're going to evaluate for the sine or the cosine of this angle, really what we're going to use instead is this reference angle. And so given the fact that we want to find, say, the cosine of 120 degrees, which, you know, it's this angle that terminates in the second quadrant, it'd be the same thing as the cosine of 60 degrees, or in other words, a half. So what we get here is 64 times a half, and with respect to what kind of a half this would be, I noticed that because our angle terminated in the second quadrant, the cosine value would have to be negative. And then with respect to what we get over here, we get 64 times the sine of 120 degrees times I. The sine of 120 would be the same as the sine of its reference angle, 60. The sine of 60 is root 3 over 2. And with respect to this value here, because our angle terminated in the second quadrant and we were finding sine there, this would be a positive value here. And so in terms of our overall values here in rectangular form, we see that our r cosine of theta comes out to be 32 times a half, or sorry, 64 times negative a half, which ends up getting us a negative 32. And then over here we get 64 times root 3 over 2. We could see that our 64 and our 2 cross cancel here, kind of like these did over here. You know, we get a 32 on top and a 1 on the bottom. So multiplying straight across now, looks like we get 32 root 3. Let me try that again here. 32 root 3 over 1. So I'll go ahead and write 32 root 3. and we'll say I. So this number here, this is our rectangular form of this number. And just to recall how we got this here, basically we took our abbreviated polar form and wrote it out into the elongated form, distributed these values through, and we're able to determine the r cosine of theta and the r sine of theta just by evaluating. So for this last example here, what I want you to try to do is take this number 32 CIS 150. So that'd be 32 cosine of 150 degrees plus I times the sine of 150 degrees. And let's rewrite this into rectangular form. When you're ready to take a look at the answer, go ahead and hit play on your video here. I would say distributing this, we get 32 cosine of 150 plus I times 32 times the sine of 150. Now with respect to 150 degrees is right here. Of course, 150 degrees is 30 degrees shy of our x-axis here. So we can see that this angle has a 30-degree reference angle here. So to evaluate for the cosine of 150, we'd really do the cosine of 30 degrees, which of course is root 3 over 2. So we get root 3 over 2. And because this angle terminates in the second quadrant, and cosine's negative in the second quadrant, only sine is positive, we're going to call this a negative root 3 over 2. And then over here we'll say I times, and we'll say 32 times the sine of 150, which really, again, we would do the sine of 30, its reference angle, which comes out to be a half. But we see that this sine value is positive up here in the second quadrant. So let's clean this up a little bit here. I noticed that when these two factors get multiplied here, our 2 and our 32 cross cancel, and we get left with a negative 16 root 3 plus now, and we get 32 times a half, that's really 16, so we get 16I. And so this is our second complex result written in rectangular form here. And so that would be how we would convert back from our polar answers back into rectangular form once you've used, say, DeMoivre's theorem. Cheers.